Good morning and welcome to this next lecture on sound and structural vibration. We were looking at approximating a radiating panel using monopoles, and we had formulated the closed form formula for power, which had 4 terms, and we were looking at the second term here. So, the second term looks like this. The second term looks like this, okay, and m goes from 1 to 3, 1 to 3. Okay. So, we had looked at m equal to 1 here, m equal to 2 here, and m equal to 3 here, and each of these demonstrate. For example, if I redraw M1 demonstrates interaction of these two, and these two. There are 3 such interactions, and 7 for 7 rows. The minus because these are alternating in sign, and 2 because there are 2 cells involved. Then for m equal to 2, these are interactions with one gap, this interaction and this interaction. In a row there are only 2 such interactions, but there are 7 rows, and there is no sign change because this is plus and that is plus. So, I have a positive and this 2 for 2 cells. And lastly, m is equal to 3, then I have interaction with 2 cells gap, gap of 2 cells. Okay. So then again there is a negative because this is plus and this is minus for the m1 equal to 4 mode. Okay. And then there is only one such interaction. Okay. Then there are 7 rows for it, okay, and 2 cells. So, that is the second term. Okay. Now, what is an interaction? One could ask. It's either you can think of this cell here applies a pressure, generates a pressure which sits on the other cell. So, other cell sees that pressure in addition to the mean pressure in the medium, and so that cell has to work against the pressure applied by this. So, you could think of an interaction of that form, or you could think that this panel is of course radiating, okay, and then this generates a pressure in the receiver point, this cell generates a pressure at the receiver point, those two add up. So, you can think of it that as an interaction, okay, but the pressure applied on the cell is what I like. So, that's what interaction means. Okay. There is a pressure seen by one cell due to another cell, and it has to work against that. So, that is what is interaction. Okay. Now, the next third term, term 3. Okay. Term 3 looks like this, summation n, this time going from 1 to n1 minus 1, which is 6, then twice minus 1 to the power n, m1 which is 4 into n1 minus n, and sine nkb over nkb. Okay, I will not repeat too much here, it is intuitive now. Okay. So, if we have these cells, one, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, okay, 4 by 7. Okay. So, now let us see the first term. First term is n is equal to 1. So, 2 minus 1 to the power 1 into 4 into 7 minus 1, which is 6. and sine kb over kb. Okay, so this speaks of interactions of neighboring cells plus minus plus minus plus minus plus, let's say. So you have neighboring interactions 1, 2, 3, 4, 5, 6, that is the 6th number. Okay, it happens 4 times, 1, 2, 3, 4, 4 columns. And the minus because there is a sign change across the node line, and then 2 because of 2 cells. Okay. Similarly, next term is twice minus 1 to the power 2 4 into 5 sine 2 kb by 2 kb. So these are interactions with a 1 cell gap. Okay. So this is 1 interaction, 2 interaction, 3, 4 and 5. There are 5 such interactions, 4 such columns, and this time there is no sign change. This is plus, then that is plus, and so forth, and there are 2 cells and further on. Okay, that's the third term. Now these were regular interactions. Let me give it that name, regular, row wise, column wise. Okay. The last term you have is a summation m equal to 1 to m minus 1 is 3, summation n equal to 1 to n1 minus 1 which is 6, 4 times minus 1 to the power m plus n into m1 minus m into n1 minus n, then sine kr by kr. Okay. So what is this now? In simple terms, this is all other interactions. All other interactions, all kinds of interactions between cells. Okay. For example, we have decided to place the location at corners, right? This corner, this corner. Okay, all the left lower corner is the cell location. So this interaction with this cell, this interaction with that cell, this interaction with that cell, and so forth. If there are any repetitions, they are accounted for. And so this r distance is now, so if we are looking at this to this, that is the r distance. If you are looking at this to this, that is the appropriate r. Okay. So I'll show you one of these, and the others should be followed in the same manner. So let us say that m is equal to 1. So let's see here. I keep drawing this picture repeatedly. One, 2, 3, 4, 5, 6, 7. Okay. So let us say m equal to 1. Okay. So then we get what? The term is summation n goes from 1 to 6, 4 minus 1, 1 plus n into 3 into 7 minus n and sine whatever kr by kr. Okay, then suppose n is 1, first term, how does it look like? I get 4 minus 1 squared into 3 into 6 and sine something kr by kr. Okay, a to k, a and b. Okay, kr is what? Square root of a square plus b square. R, that is r. Okay, because m is 1, n is 1. Okay, so r is typically square root of m square a square plus n square b square, that is r. Okay, so now what is this? What is this interaction? We have not row wise but this interaction with that. That means this cell interacts with that cell. Okay, and this cell interacts with this cell. This is this cell interaction. Then this cell interacts with this cell, and then this interaction. Okay, so now how many do we have? 1, 2, 3. We have 3 interactions. Okay, now let us look at this. We have 3, 6. 3, 6 are 18, 18 for 72. Okay, so if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? Then, okay, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 36. Okay, and then 2 cells, that's 72. And positive. Why positive? Because this is so say plus minus, then minus plus minus plus. So you are having a plus interaction with a plus interaction, hence plus. So this sign is plus, this sign is plus. Okay, and the distance is from here to here, which is square root of a square plus b square. Okay, so the 4th term describes all other interactions. So this does give insight into how cells interact. Okay, interact. Now let's see here. I'll give you one more insight here. Suppose I take this case to demonstrate. I want a small case to demonstrate m1 is 3 and n1 is 3. Okay, so it's a 3 by 3 mode. Okay, 3 mode, sorry. Okay, and we are at very low frequency, very low frequency. We said that the entire panel is equal to 1 cell, should be equal to 1 cell, right? So if I write the formula, let me write the formula. Okay, the formula for power, outside there was a constant representing 1 cell, and inside I have m1 n1 which is 9. Then I have a sum that goes from 1 to m1 minus 1 which is 2, then twice minus 1 to the power m n1 which is 3, then m1 minus m3 minus m, and sine mka over mka plus summation over n equal to 1 to n1 minus 1, which is 2, then twice minus 1 to the power n, m1 which is 3, n1 minus 1, 3 minus n, into sine nkb by nkb, and finally the double sum plus the double sum 1 to 2, 1 to 2, 4 times minus 1 to the power m plus n, 3 minus m, 3 minus n, sine of kr by kr. Okay. Now let us say we are at a very low frequency, that means k, which is omega by c, is very small, very small. Then I have a sine of a small radian quantity, so it is that argument itself, so it is mka, sine of mka is mka. Then that mka cancels with denominator mka, so I get a 1 here. Similarly I get a 1 here, and similarly I get a 1 here. Okay, so I have to sum these up now. I have to sum these up, which I will do on the next page, and if you trust me, I will not repeat the formula, that is why. Okay. So that turns out to be here 9 plus the second term gives me 2 into minus 1 into 3 into 2 plus 2 into 3 into 1. Then the third term gives me 2 into minus 1 into 3 into 2 plus 2 into 3. The fourth term gives me 4 into 2 into 2 plus 4 into minus 1 into 2 into 1 plus 4 into minus 1 into 2 into 1 plus 4. These are the 4 terms. So what do I get here? I get a 9 here, I get a 6 to 12 minus 12 here, I get a plus 6 here, I get a minus 12 here, plus 6 here, I get 16 minus 8 plus 4. Okay, this 20 minus 16, I get 4 from here, I get a minus 6 from here. So 9 minus 6 plus 4 is 1. So at low frequencies it is 1 cell. Okay. So we will see more of this, we will get some further insights. The next topic I would like to start is this paper called, the title, Response of Ribbed Panels to Reverberant Acoustic Fields by G. Majdanek. It is a Journal of Acoustical Society of America paper. volume 34 part 6, year is 1962. It's a very important key paper in panel or plate sound radiation. Okay, set in a baffle. Okay, in a baffle. This is where Maidanik presents radiation resistance. Okay, okay, so this mean square velocity, okay, into radiation resistance is sound power. Okay, that's how radiation resistance is defined. So he presents radiation resistance formulas. Okay, and formulas closed form. Okay, obviously closed form approximations. Okay, appropriate for various modes and frequency ranges. Okay, so now this is also the paper where mode classification was done. Mode classification. That is modes differentiated as corner radiators, edge radiators, then double edge radiators, okay, then acoustically fast radiators. Okay, so here so this is very similar to radiation efficiency, okay, except for some okay, radiation efficiency is power radiated divided by rho CS P tilde PQ square. Okay, so power divided by this, so power divided by this entity is your radiation resistance. So radiation efficiency into rho CS is radiation resistance. Okay, so he presents radiation resistance. So this is modal, mode by mode, okay, modal. Okay, so you have an MN mode on a plate, MN mode on a plate of dimensions A comma B dimensions. Okay, that means your Kx mode is M pi by A and the Ky mode is N pi by B. Okay, the plate lies in the XY plane. So these are the modal wave numbers. You should now distinguish, okay, modal wave numbers as opposed to the Kp or Kb, which is the free plate wave number. and K, which is the acoustic wave number. You should know these now by now. Okay. So for every mode, so modal radiation resistance is presented from low frequency to just beyond the modal coincidence. That means K being equal to square root of Kpx square plus Kpy square, just beyond. Okay. Okay. Along with this, so we'll see. So we'll see. So he first formulates a central integral, a central main integral for modal radiation resistance. And from there he starts to approximate various cases. Okay. And so we will derive this central integral, okay, because it's a bit convoluted. Okay, we will derive it from start. Okay. Then what next? Let me just mention it, is that this is just modal, okay, but in a realistic situation several modes contribute to the response. So there he computes or presents again a formula for modal averaged radiation resistance. Okay, we will see somewhat of this also later. Okay, time is up for this lecture. I will close here. Thank you.